All right, the purpose of this video is to highlight some of the salient points of the lecture slides for the Pulmonary 2 lecture. The objective of this video is to describe the similarities and differences between pulmonary volumes and capacities, explain pressure curves for the great vessels and some heart chambers, describe blood flow mechanics in the lungs, explain the relationship of hydrostatic and osmotic pressures in the vessels, particularly the pulmonary capillaries, with regard to fluid volume and balance, and finally explain the mechanisms of oxygen and carbon dioxide movement across the respiratory membrane. This figure just illustrates the fact that there are two respiration mechanisms. One is external, in which we are moving oxygen from the air into the blood and carbon dioxide from the blood into the air. And so this part refers to the heart-lungs part of respiration. In internal respiration, we're going to do the opposite. We're going to diffuse oxygen from the blood into the body cells and carbon dioxide from the body cells into the blood. So that's represented here. That external respiration is emphasized in this figure, in that air goes through the upper airway and into the lower airway via the nasal cavity and via the oral cavity. And when air comes through these cavities into the pharynx, into the trachea, through the carina and the main stem bronchi, and into the terminal passageways, we now are looking at this in the respiratory bronchioles and also the alveoli, but this diagram primarily emphasizes the alveoli. And it's just basically saying the same thing, that we're exchanging carbon dioxide and oxygen. So let's turn our attention briefly to the volumes and the capacities in the lung. The diagram on the right represents a spirometry graph that is showing the inspirations and expirations as a function of time. The red curve shows the different inspirations and expirations. Inspiration is represented by an increase in lung volume of air, and expiration is represented by a decrease in lung volume of air. I want to draw your attention to the tidal volume, which is the amount of volume in which you are inspiring and expiring during a normal breath. And you can see that its extent is at about 500 milliliters, but it starts at about a little over 2,000 and a little under 3,000, give or take, in terms of the amount of volume that's going in and out of the lungs. You'll also notice that there's an inspiratory reserve volume, and that is if you were to take a forced inspiration, the maximum you could inspire is about 3,000 milliliters, a little under 3,000 milliliters. So the complete volume that the lung could go to is a little under 6,000 milliliters. If you were to take a forced expiration, that is the expiratory reserve volume, and that is about 1,100 milliliters. And then finally, there's a residual volume of air that always remains in the lungs regardless of how much you try to expire, and that is about 1,200 milliliters. And that accounts for the fact that the lungs are always at least partially inflated by virtue of the fact that the pleura are stuck together, both the visceral and the parietal pleura. Now we can take these volumes and we can add them together mathematically, and that's where you get your capacities. So inspiratory capacity, the functional residual capacity, the vital capacity, the total lung capacity are all shown there on the right. One thing to keep in mind is that the volumes and capacities are about 20 to 25% less in women than they are in men, and greater in large and athletic people than in smaller individuals. So if I took these capacities, they're really simple equations that can be derived. I just noticed that VT here should be tidal volume. There we go. Sorry about the typo. And again, it's simple math, but these volumes are involved in terms of the results that you would see from a spirometry test. So you should know these equations. Okay, let's take a slight detour, and now we're going to talk about the blood. Let's first talk about the pulmonary arteries. You'll notice that the pulmonary artery pressure is much lower than the aortic pressure, and that becomes important. If the pulmonary pressures were to go up too high or too low, then there's probably something going on with the heart chambers or with the lungs clinically. So notice this number. The pulmonary circulation has lower pressure than the systemic circulation. It's about 18 millimeters of mercury below. I am probably just going to refer to those pressures as millimeters, or just use the numbers from here on out. Let's look at the right ventricle. So this curve shows the right ventricle in black and how it actually compares with the pulmonary artery and what we saw with the aortic pressure. Here is an important number. The systolic pressure in the right ventricle of a normal human averages to about 25 millimeters, and at systole, which we'll learn more about later. And the diastolic pressure, which we'll learn more about, diastole, which we'll learn about more later, that pressure averages to 0 to 1 millimeter. And that becomes important later, particularly as we expand this curve and we look at it here. This is a graph that you're going to see quite a bit. Just to give you some orientation, volume is shown here at the bottom of the graph. Pressure is shown here at the top. The electrocardiogram, which you are probably already familiar with, the PQRST curve, is down here at the bottom, and this shows us a reference for what's happening electrically in the heart as we have changes in pressures and volumes. The phonocardiogram, or what you would auscultate, is shown here at the very bottom. As we move up the graph on the right, the ventricular volume is shown in blue, the ventricular pressure is shown in red, the atrial pressure is shown in dotted black, the first dotted black line, the aortic pressure is shown in the upper dotted black line. Some things to point out is that there's a little blip that happens here, and we saw it in this curve, but I didn't point it out, right here and right here. That refers to the place where the aortic valve and the atrioventricular valves open and close. Notice there's a little difference in when the aortic valve is closing and the AV valve is opening, and vice versa on this side. So the bottom line of this figure that I'd like you to appreciate is that the aortic pressure follows the ventricular pressure at its apex. And you can see that right here and right here. We'll get more into detail in terms of the volume contractions, ejections, relaxations, and flow later, but this diagram nicely shows how this correlates together. I think that's all I want to talk about this diagram for now, but you'll find it to be a really useful reference throughout your career. Okay, let's go back to the pressures in the pulmonary vessels. Again, the systolic pulmonary arterial pressure averages 25 millimeters, and the diastolic pressure is about 8 millimeters, which makes the mean about 15 millimeters, and you can see that here on the pressure curve on the left. By the time the blood makes it to pulmonary capillaries, notice that the pressure is slightly lower than the diastolic arterial pressure. So it dips from about 8 millimeters down to 7, and is reflected right there. By the time the blood returns to the left atrium, notice how much the pressure has dropped from about 7 millimeters down to almost 2 millimeters. Okay, now let's talk about the blood volume in the lungs. This curve shows that if you pay attention to the red line, this curve is showing the amount of blood, relatively speaking, between the top, middle, and bottom lung fields. As you can see, the bottom lung field has the most amount of blood in it at any one time, typically when a person is either standing or sitting in orthostatic position. Once the person exercises, notice that the entire curve shifts up, or in other words, more of the lung is filling with blood, which makes sense. The heart increases in terms of its rate of beating and its volume, and so you'd expect to see that. But if we extend this line to the left, at the peak of the volume of the blood in the lungs, notice that the top of the lung has about the same volume that the bottom of the lung would have had at rest when someone's exercising. Okay, let's switch gears to pulmonary flow mechanics. Here we're talking about zone 1, zone 2, and zone 3 blood flow into the lungs. This is different than the previous diagram, which showed top, middle, and bottom lung fields. Here we're talking about the essentially the flow going through the capillaries in the lungs. So let me start with zone 3. Zone 3 is continuous flow. And what that means is that the arterial pressure and the pulmonary pressure remain greater than the alveolar pressure, air pressure at all times. So if you look at the diagram, on the left is the incoming artery, and on the right is the outgoing vein. Notice that the pulmonary artery, or arterial to capillary at this point, is blue, representing relatively deoxygenated blood, and the vein is relatively red, representing that it's more oxygenated. The partial pressure of the alveolus is represented here, and the partial pressure of the capillary is represented here. So as blood flows into the capillary bed in this direction, it has continuous free flow, and the pressure that's coming from the vessel is always greater than the pressure that's in the surrounding alveolus. That's zone 3. In zone 2, as you can see here, this is called intermittent flow, where the systolic arterial pressure is higher than the alveolar air pressure, but the diastolic arterial pressure falls below the alveolar air pressure. Okay, so basically there is less pressure going through the alveoli than there would be in zone 3. In zone 1, this is where there's no flow. So there's no, the alveolar air pressure is actually greater than the arterial pressure coming in. Okay, so why does that make a difference? Let's go to a clean figure here. Basically, the bottom line is that your lungs are always going to be in a zone 3 or in a zone 2 zone 2 or zone 3 flow mechanics right here. Okay, and one of the things to keep in mind is what's noted in the text to the left. In the lower regions of the lungs, because you have more blood flow through there, and that's what you're using more often, you're going to be in a zone 3 flow almost all the time. All right, now if somebody is in orthostatic position, sitting up or lying down, the bottom lung fields here is what we're talking about. But if the person now lies down, now the apex, or the top of the lungs, will also have zone 2 or zone 3 flow. And that's simply because of gravity. That's simply because of the position of the heart relative to the anatomy of the lungs. So you can imagine that it might be super important to be able to move people from a lying down position to at least a sitting up position frequently in order to be able to move around the zones of the lungs and allow the heart to work easily. It's also, if you think about it, one of the reasons why it might be good for people to lie down if they're having pressure issues. That doesn't summarize all of that, but that's another way to look at it. Okay. Zone 1 only occurs in abnormal conditions, and so that basically means that during the cardiac cycle there just isn't enough flow going through the lungs to be able to exchange gas. And then finally, as you talk about pulmonary flow, going back to exercise, this graph shows that as the cardiac output increases, then the pulmonary arterial pressure increases, and I think we already knew that, but as the exercise goes up, then that pulmonary pressure goes up as well. Okay, let's switch gears now and let's talk about the lymphatic system. This is an overview diagram showing that the heart pumps blood via the pulmonary arteries into the lungs, which comes back via the pulmonary veins, and what is actually happening to the fluid that is within the interstitium of the lungs. Let's refer to this diagram. So now we're talking about pressures of fluid. The capillary on the left shows hydrostatic pressure numbers, and these numbers are important, by the way, and osmotic pressure numbers. Notice that the hydrostatic pressure is going to want to push fluid out of the capillary, but the osmotic pressure is going to want to bring fluid back into the capillary. Hydrostatic pressure caused by the pressure from the arterial system. The osmotic pressure caused by the amount of solutes that are in the blood. You add these numbers up, and what you get is a positive flow going out of the capillary. In the alveolus, we have a net zero pressure between the inside of the alveolus and the outside of the alveolus. Notice that they're both at -8. So the only thing that would cause any sort of movement of fluid into the alveolus is actually by evaporation, and it's really not that much. So what is the result of this? If we're constantly pumping fluid volume into the interstitial space, which is defined by the space where the cells reside in this region, then we are going to continually increase the fluid and cause an edematous condition. So that's not good. So what do we have? We have the lymphatic vessels, which, as you can see here, have a negative pressure, which essentially sucks fluid into those vessels. So where does that fluid go? Well, the fluid goes into the lymphatic vessels from the lungs, and on the left side of the body enters into the thoracic duct, which is located here, and enters into the junction of the internal jugular vein and the subclavian vein into this vessel essentially right here called the left brachiocephalic vein. On the right side, the lungs drain its lymph into here, into the right lymphatic duct. So this is the thoracic duct on the left and the right lymphatic duct on the right. So what happens if we just talk about the lungs is that the heart pumps fluid to the lungs, but the fluid that comes back to the heart, if we just talk about the heart and the cardiovascular system, the fluid that comes back to the heart is actually lower in volume than what came out. But in reality, what happens is that because of the lymphatic system, the output and the return of fluid volume to the heart is equal, because the lymphatics help return that excess fluid that is in the interstitial space back into the venous system of the heart. So basically, we are tricking the heart by letting it think that the volume out is equal to volume in, and we're doing that because of the lymphatic system that takes care of the net positive pressure that is going out into the interstitial space. I think that's pretty clever. It's one of my favorite systems in the entire body. It's very cool. So what happens if these capillaries or membranes, we're going to talk more about the respiratory membrane in a minute, but what happens when these things are damaged? Well, besides the fact that you have the inability to exchange gases, you also have the inability to remain isovolumetric, which is not a good thing. Okay, let's transition now to the respiratory membrane. The image here on the right simply shows that we have lots of pockets of alveoli, and between the alveoli are all these capillaries, tons of capillaries, larger veins and arteries and lymphatic vessels and bigger interstitial spaces. But the bottom line is that we have, if we take this image and we look at let's say this one, and we bring it down to here, what we are looking at now is the respiratory membrane, which is comprised of a number of layers. Let's take it from the alveolus to the capillary. So the first layer we have is a fluid layer, and it's comprised of surfactant, which you might remember is produced by the type 2 alveolar cells. That layer of surfactant lines the alveolar epithelium, which is produced by, or actually comprised of, the type 1 alveolar cells. So these are type 2, produced by type 2, and this is comprised of type 1. Okay, or they're also called pneumocytes. Each of the pneumocytes is on a basement membrane. Basement membranes are adjacent to the capillary basement membrane via the interstitial space, which is filled with connective tissue. And then the capillary endothelium, which is the epithelium of the vessel that sits on its basement membrane, lines the capillary. And then inside the capillary, you have our red blood cell. So that respiratory membrane is actually comprised of 1, 2, 3, 4, 5, 6 very, very thin layers. And it's an important membrane. So it is the membrane that allows the diffusion of oxygen and carbon dioxide across it. Okay, so from this diagram, you can probably readily understand that the ability of gas to pass through this respiratory membrane depends on a few things. The first is the thickness of the entire membrane. So if any one of these 1, 2, 3, 4, 5, 6 layers is thicker than it should be, or if all 6 of them are thick or thin, that determines how fast the gas can perfuse through the membrane. The surface area of the membrane refers to how much area a capillary will contact, or capillaries will contact with the respiratory membrane. So if we have a respiratory membrane that is degenerating, but we haven't changed the number of capillaries, then we have a decreased surface area for the capillaries to contact the respiration membrane. The diffusion coefficient of gas we'll go over in a minute, but how fast the gas can travel through these membranes makes a huge difference in how readily it will pass. And oxygen and carbon dioxide have different diffusion coefficients. And then finally, the partial pressure difference of the gas between the two sides. We refer to partial pressure because the pressure due to, say, let's just use oxygen for example, the pressure due to oxygen relative to the other gases that are in that air or fluid is its partial pressure, or the partial contribution of that gas to the total pressure. So anyway, the pressure makes a big difference because the only way we're able to move gases is through osmosis. Is through diffusion. Okay, so let's talk about our partial pressures for oxygen and carbon dioxide. What these two graphs essentially say is on the left we're talking about oxygen, on the right we're talking about carbon dioxide, and we are interested in this dot right here saying that the partial pressure of oxygen in the alveoli is a little bit above 100 millimeters, whereas the partial pressure of carbon dioxide in the alveoli is a little bit below 50. And we'll get to some specific numbers in a minute. Okay, the graph on the right talks about the diffusing capacity. And the bottom line that you should appreciate here is that the carbon dioxide diffuses much faster than oxygen, whether at resting or exercise. So here is the difference between resting between carbon dioxide and oxygen, and here's the difference between exercise between carbon dioxide and oxygen. And notice that carbon dioxide just simply diffuses more readily. Okay, so now let's talk about how gases exchange based on their partial pressures. We'll start with oxygen. So in the alveolus, the partial pressure of oxygen is 104 millimeters. So that's a little bit above 100 that we were referring to earlier. The partial pressure of oxygen in the entering pulmonary capillary is at 40 millimeters. And so just based on this, you would expect oxygen to move from the alveolus into the capillary. So you can see that here in the graph below. The blood partial pressure is at 40, but as we go through the x-axis is actually distance into the capillary. As we move into the capillary, we start equalizing with the amount of partial pressure between the alveolus and the capillary. Notice that we're not actually going to decrease the partial pressure of oxygen in the alveolus. It stays at 104 millimeters, and that's because you're constantly breathing air. Now, as that oxygen moves into the body, the partial pressure starts decreasing a little bit, not by much, but 95 millimeters, and that's because it's diffused a little bit here and there through the endothelial membrane and other reasons. But the bottom line is that because it is at such a high pressure, relative to the interstitial space that's surrounding the cells, it will diffuse from the capillary into the cells. So it's shown here that the interstitial fluid that's surrounding the tissue only averages 40 millimeters, and that pressure is going to drive oxygen into this space. Okay. All right. So what ends up, here's the equation. So the partial pressure in the interstitial fluid is 40 and tissue cells is 23. So oxygen will go from the capillary into the interstitial space into the cells. Right? So we're going down a diffusion gradient. Very simple. So what ends up happening is that on the venous end of the capillary, the partial pressure of oxygen is now 40 millimeters. Okay. Now let's talk about carbon dioxide. So carbon dioxide is being used by the cells, and carbon dioxide is going to want to diffuse from the cells to the interstitium to the capillaries. Okay. Now, the elevated tissue cell partial pressure carbon dioxide diffuses very easily, even though the difference in the partial pressures is very, very small. So the entering partial pressure of carbon dioxide is at 40 millimeters. We're still going down a diffusion gradient, 46 to 45 to 40, and it will equalize at 45 millimeters. But the reason why we don't need a huge amount of pressure is because carbon dioxide diffuses very, very readily. So now let's go all the way back into the lungs. the partial pressure of carbon dioxide in the blood is 45, but the partial pressure of carbon dioxide in the air and the alveolus is only 40. And yet, because carbon dioxide moves really easily, it can move readily from a 45 to a 40 partial pressure across the membrane. Okay, that was a lot, but I think this stuff is super cool in terms of how gases can move based on partial pressures, based on the volumes of blood that are perfusing through the lungs, based on the pressures. It's super cool stuff. Okay, I think that's it for now. Thanks a lot.